To the untrained eye, the periodic table is incredibly dense. It looks like a chaotic blur of letters, numbers, and rigid boxes that seems to require years of tedious memorization to master. Yet scientists look at this exact same grid and instantly predict the invisible structure and behavior of elements they have never even touched. Scientists organize these elements onto a dual-axis coordinate system, where an element's position dictates its properties. Once you know how to read these intersecting coordinates, the hidden rules governing physical matter snap clearly into focus. Navigating this map begins with the legend, which we can find by isolating a single coordinate box. Looking at this diagram of the hydrogen box, we find the basic data points: the chemical symbol, the element's full name, and its atomic mass. But the most vital metric is the atomic number at the top. This integer represents the exact number of protons sitting inside that atom's nucleus. If we move to a second coordinate, helium, the atomic number ticks up to 2, signaling that a second proton has been added to the core. This simple principle dictates the layout of the entire board. Every element is arranged sequentially by its increasing atomic number. The map also uses broad color coding to group the elements, allowing you to quickly differentiate the metals from the nonmetals. By checking a single box, you secure the precise atomic fingerprint of an element before you even consider its position on the wider grid. Zooming out to the full table, we can examine the overarching architecture of the columns and the rows. The vertical columns are known as groups. All elements stacked within a single group share similar behavioral characteristics. Here we see a 2D model of an atom. Notice the bright outer ring. These are the valence electrons, the electrons occupying the outermost shell. These specific electrons dictate how an element will bond with other atoms. You can find that valence number using a quick navigational trick. Count the groups from left to right, skipping over the complex transition metals in the middle. Group 1 has 1 valence electron, Group 2 has 2, and so on. Then we have the horizontal rows, which are known as periods. Moving downward through these rows determines the total number of electron shells. Dropping down a period adds a new electron shell to the atom structure. Pinpointing an element's x and y coordinates reveals its physical anatomy and its potential to connect with other matter. Because the board is built on such strict structural logic, moving across the grid causes distinct physical properties to reliably shift. The first major trend tracks atomic radius, or the physical size of the atom. This grid tracks how that radius changes. As you navigate downward through the periods, the size of the atom steadily grows. Conversely, tracing a path left to right across the groups compresses that radius, making the atoms progressively shrink. A second major trend tracks ionization energy. This is a measurement of how readily an atom will allow one of its electrons to be removed. As your path moves downward through the periods, the ionization energy decreases. The atom holds its electrons loosely. But if you trace from left to right across the groups, that energy spikes. The atom grips its electrons tightly. Following these directional paths exposes a clean, inverse relationship between an atom's physical size and its grip on its outermost electrons. What initially appears as a wall of chaotic boxes is actually a synchronized system of moving parts. Chemists use these coordinate boxes to determine an atom's internal structure without ever needing to look through a microscope. You can apply this same predictive blueprint in your own classroom to anticipate how elements will react before mixing a single chemical. This grid provides a master blueprint for predicting the structural rules and bonding behaviors of the elements.